Okay guys, you've been asking for this video for a while, but since tomorrow is the AP exam and a lot of you need some extra studying, here is my AP Physics 1 exam review. So in the description below there will be a document that will allow you to, it won't allow you to do anything. You'll have to copy the document and you'll be able to take notes using that document, okay? About this. There's a box for each topic on here. And there will be links to the other videos that I have already done on there as well. Now, this is just a refresher, a quick review. This is not the only study tool you should use. I suggest using the actual College Board exam materials that they have online, as well as Khan Academy and other resources you can find either online, within your textbook, or from your classroom. Okay? So let's get started with one-dimensional motion. So regarding one-dimensional motion, there are really only 5 things that are important, and those are the big 5 equations. Now, you can see this on my website, which I will leave in the description as well, because I go into an in-depth discussion about one-dimensional motion and how these 5 kinematic equations, which kinematics just means the study of kinetic motion, and how they are produced as well as how they were discovered. So let's list out the big 5. So the first one is going to be V final, which is the final velocity, is equal to the initial velocity plus the acceleration times the time. Okay? The next one is going to be delta x, which is the displacement or the change in distance, is equal to v average, which is the average velocity, which is actually equal to v final plus v initial over 2 times the time. So in other words, you can just say that this is equal to v final plus v initial over 2 times the time. Okay? 3 is going to be delta x is equal to v initial t plus 1/2 a t squared. 4 delta x is equal to v final t minus 1/2 a t squared. And the last one is v final squared minus v initial squared is equal to 2a delta x. Those are your 5 kinematic equations, and you will use these a lot regarding simple motion. Now, I suggest that you should go to my website and look at how to find these, how to use these as well, and what everything means. This is just a refresher course, of course, because if I were to go into detail on everything, then this would be easily a 2-3 hour long video, which I do not have the time for. So that means that one-dimensional motion is done. Now, the next one is two-dimensional motion, but since I've already done a video on two-dimensional motion, you can go to that video, which should be in the physics playlist on my YouTube page. So we'll consider this one done as well. It's also on my website as well if you want to take a look at that. I actually haven't updated it in a while since I've been very busy, but I've been updating my YouTube channel quite frequently. So you should see a bunch of videos. I think you should see one on forces. There's actually 2 videos on forces. You should see one on linear momentum. You should see one on SHM and waves. So the only things that I actually have left to discuss in this video are work, energy, and power, which is what WEP stands for, circular motion and gravitation, as well as electricity. Now, if you want to look at waves, SHM, which is simple harmonic motion, linear momentum, two-dimensional motion, forces, and all that stuff, then either look at my website, it shouldn't be that updated, so it should only have up to like work, energy, and power. Look at my YouTube videos. because I already have a physics playlist of all these things. And I suggest that you watch those videos and take the notes using the document that's in the description of this video. Okay, so now that these ones are already done for you, as you can tell, because I did them in preparation for the unit tests, as well as preparation in the future for this AP exam that happens to be tomorrow, we will go over the ones that I have not covered. So the one that I haven't covered yet is work, energy, and power. So this one is fairly standard. Work, which is W, is just the amount of force that is applied onto an object over a certain distance. So we'll call this F, we'll say delta X. Because it's not really delta X, it's really just X. So we'll say that work we'll just do delta X anyways, just for simplicity. Now, this symbol on the top represents a vector, which just means that it has direction. If you want to remove the direction, then you can just think about it like this. So say that you have this, right? This is your angle, and this angle can be anything from 0 to 360 degrees. And this is your triangle. Your triangle could look something like this as well, and this is still your theta, and that this is our theta here. Okay? So say that this right here is our x. Okay? And this is our theta. Well, this is the direction, we'll say, that the force is applied. So say you have your free body diagram, right? This is your free body diagram. This is the direction in which the force is applied. Well, you can just say that this is a force vector, and this is a force vector, and the resultant of those two force vectors is this force vector right here. Okay? So all we need to do to find x is just do F, the force applied, right, which is the hypotenuse. To find x, we would say x is equal to cosine F applied times cosine theta. Okay? So in this case, we know that this is true. So we could just say that x will replace with d. And since now we've given this a direction, cosine theta, we no longer need the vector on it because we're not specifying a direction. This is the direction. So we no longer need to specify using the symbol. So in other words, we could say that since d is equal to x, which is equal to this, right? We could just say, all right, that means that work is equal to the force times the distance times cosine theta. Because this is the force that we want right here. Well, this isn't really x, this is F, which is like this. So this is the force that is applied horizontally. So we'll say that this is Fx. Okay, and since this is the direction, we no longer need the little line on the top. So we can just say this. And we can say x is equal to d, since we no longer need the vector form, since we're already specifying direction through this through cosine theta. So, that is work. But work also is a change in kinetic energy. What is kinetic energy? Kinetic energy is the energy of motion. The energy, or you can't define energy and work interchangeably. You have to use some. It is essentially just the work done upon an object in order for it to move. So we define kinetic energy as such. K, which stands for kinetic energy, is equal to half the mass times the velocity squared. And the opposite of that, which is potential energy represented by U, is equal to, mgh. Now this is for an object. For a spring, it's a little bit different. The kinetic energy of a spring is equal to negative U spring. Okay? It's negative this. And the U spring, which is just the potential energy of the spring, instead of being mgh, is 1/2 kx squared. K is the spring constant. Work can be defined as the change in kinetic energy. So we could say work is equal to delta K. Now, what is the unit of measure for these things? Well, it's joules, which is essentially just a Newton meter. And a Newton is a kilogram, so is a kilogram meter per second squared. So this is a kilogram meter squared per second squared. Now, power is work over time. So this is actually in watts, which is a joule meter. Not a joule meter, a joule per second, which is the same thing as a kilogram meter squared over second cubed. And the power is just the measure of work applied over a certain time. So that's how like microwaves are measured. How many watts? So the power of a microwave depends on how much work it can do onto your food over a certain period of time that you set. So that is work, energy, and power. Circular motion and gravitation. This one is fairly simple. So you remember the sum of forces is equal to ma, right? Well, what if your object isn't accelerating linearly like this, right? It's not experiencing any change in velocity. Instead, it's accelerating not because it's changing velocity, but because its direction is changing, like in a circle. It has a constant speed, but it's accelerating because it's going around the circle, which means that its distance, if you were to stretch this out, would look something like this. A curve. In this case, this is a sinusoidal. So this isn't really A, this is a C, which is centripetal acceleration, because this is accelerating not because there's a force going this way or tangent. The velocity is tangent, so we call this a tangential velocity. However, this tangential velocity is not caused by a force. Instead, it's caused by a single applied force that has then disappeared, and then this is the actual force that drives the motion. There is a force of, there's some force going towards here that causes this object to orbit around it in a circular motion. So the definition of centripetal acceleration is the velocity squared over the radius. Now, this also relates to another concept known as gravitation. Gravitation is essentially just the measure of gravity. So the force of gravity, we know on Earth that the force of gravity is equal to mg, which is your weight. Now, how do we calculate mg? Why do we know that g is 9.8 meters per second squared? 9.81 meters per second squared, to be more specific. Well, it's because the force of gravity on a certain planet is equal to, and we'll call that planet X, okay, is equal to the universal gravitational constant. You can look that one up. I don't remember it off the bat of my head, but I believe it will be in your formula sheet, which will be on your test, times the mass of the planet times the mass of the object that it is working on, that it is gravitationally interacting with, over the radius squared. The radius, well, we'll not say radius. We'll say the distance squared, meaning the distance between the center of mass of the object and the planet. So this would be d, which is the distance between the center of mass of the planet and the center of mass of the object. So plugging in these values, knowing the mass of the Earth, the radius of the Earth, and the mass of you can calculate that mg is equal to whatever your weight is in newtons. And then how do we get g? Well, you divide by m to both sides. We say that this is equal to m object g, which is just the weight of the object on planet X. And then you can cancel out the mass of the object, and you get that the acceleration due to gravity on planet X is just equal to g times the mass of the planet X over the distance squared. So essentially that means that the higher you are up in the atmosphere, so like if you're about 1 Earth radius up from the Earth, you will experience what change? Well, half the distance, right? So if you double the distance between you and the Earth, then that will mean that you have 1/4, or you have quartered, we'll say, this is a better term, the force of gravity upon you, which means that the acceleration due to gravity is not 10 meters per second squared, but instead 2.5 meters per second squared. So that is circular motion and gravitation. And then finally, electricity. Now, we'll start off by introducing Coulomb's law. Coulomb's law is the measure of the force of attraction or repulsion between two charged objects. So this is equal to K, which is the charge, which is Coulomb's constant, or the charge constant, which is 9 times 10 to the 9, times Q1, which is just the charge of one object, times Q2, which is the charge of the second object, divided by d squared, which is just the distance squared. Now this looks a lot like the gravitational one that we just went over. That's because Coulomb adapted this from Newton's gravitational law, or Newton's law of gravitation, to make his own law. Coulomb also discovered the charge of the electron was 1.6 times 10 to the negative 19 coulombs. So now let's get into how electricity works and how it's transferred. So imagine that you have something here that's 9 microcoulombs, and here that you have something that's -3 microcoulombs. Okay? And say these objects are actually the same size. Okay? Don't worry about how they're different sizes on the paper. Imagine that they are the same size. Now, what will the total charge be after they touch? Well, what's the total charge now? Well, total charge currently is 9 plus -3, which is 6 microcoulomb, or coulombs, however you want to pronounce it. Now, that's our total charge, okay? So what is our total charge going to be afterwards? Well, it has to be 6 microcoulombs because of the conservation of charge, which in a circuit will be known as Kirchhoff's junction rule, which is the conservation of charge. The loop rule will be a conservation of energy, but we'll get into that when we get into circuits, which will be soon as we finish talking about this concept. Now, when these two objects touch, how does the transfer of electricity flow? Well, it flows from more charge to less charge. So what will happen is once they're touched, they will stabilize at a certain point. So this will become 3 microcoulombs, and this will become 3 microcoulombs. So now the total charge is still 6 microcoulombs. However, now they have the same charge because they're the same size. If this one were more massive, it would give less to this one because it's smaller, and a more massive object should hold greater charge, so that it shares the same ratio of mass to charge. You have to have the same mass to charge ratio. So say that this object, right? So say that we still had the same charges, right? However, this object is half as large as this one. Well, the total charge is going to stay 6 microcoulombs, which is the total charge. However, it will not give 6 microcoulombs to this one, which is how much it gave before, to make 3 and 3. Instead, it will give 3, which is half. So now it will be 6 microcoulombs, and this one will be 0 microcoulombs. So now the total is still 6 microcoulombs, but the difference is the fact that it didn't give as much away. So now they share the same mass to charge ratio. Now, although this is like 6 to mass, and this is like 0 to mass, which would mean it's 0, the mass to charge ratio doesn't apply to how much charge the object holds, but instead applies to how much charge the object transfers. So now we know about the transfer of charge goes from a greater charge to a smaller charge. Well, let's talk about a battery. Now, this is the symbol for a battery on a circuit. So now let's draw a circuit. This is a light bulb. So this is the battery, this is the positive end. Charge flows from the positive end to the negative end. Now, does charge really flow from the positive end to the negative end? No. Electrons flow out of the back and through this way. However, we imagine things as current, which is the flow of charge. And since we say, based off of the transfer of charge like this, that we had just done before, that it goes from more charge to less charge. And a positive charge is greater than a negative charge, right? So it should flow like this. Well, technically, that transfer of charge we were going over before isn't the transfer of greater charge to smaller charge. In fact, it's just the movement of electrons in a way that allows, or the movement of negative charged particles in a way that seems like it's a transfer of positive charge. However, positive charge doesn't move because you never see neutrons isolated by themselves unless it's in an acidic solution. Then you see then you see protons just by themselves. So this is current. The symbol for current is I, which is in coulombs per second. So it's just the flow of charge throughout the circuit. Now, this is a light bulb. Okay, say this has a certain resistance to the flow of charge. We'll say that resistance is 3 ohms. Now, ohm is a measure of resistance, and ohm is the name of the person who discovered resistance and resistivity. Okay? Now, voltage is the potential. So say that this has 20 volts. Okay? So voltage is the charge potential, meaning the potential for charge to flow, which is measured in joules per coulomb. So the potential, meaning how much energy will flow based off of how many coulombs of charge there is. So it's basically how much energy can be produced by a certain charge or flow of charge. Now, in this definition, I is equal to V over R. We'll make this more simple by saying that the resistance is actually 4. So that means that here, the current is 20 volts, which is in joules per second, so 20 joules, not joules per second, joules per coulomb, over 4 ohms, and like that. So what does this give you? This gives you coulombs per second, which is actually an amp. So what does that mean that an ohm is equal to? An ohm is actually equal to a joule second per coulomb squared. That is what 1 ohm is. An ohm is a joule second per coulomb squared. And that is all those terms. Now let's talk about the different types of circuits. Now you have two different types of circuits. You have a series circuit, which has resistors in series. So it's like this. Charge flows throughout here, and each one hits the resistor and provides a certain voltage drop, which is a reduction in potential. Until you get back here, where the voltage was 0, and then it's recharged here, back at its original voltage. Now you can calculate the voltage drop of a series circuit quite easily by doing a resistor, and by doing the resistor number, right? So say this is R1 and this is R2, and N represents the number, times the current. And the current is constant. It's constant in a series circuit. It stays the same, and that is Kirchhoff's junction rule, because the charge has to be maintained throughout a certain circuit. Through a single circuit, the charge has to be maintained. It's conservation of charge. Now, it's actually negative, but it's fine. So the voltage drop is equal to negative times the resistance of the resistor N times the current, and the current is constant. So how do you find the current if you're only given the voltage and the two resistors? Well, you can find the current by doing the voltage divided by the total resistance. And the total resistance for a series circuit is just the sum of the resistance of each resistor in the circuit. And so the difference between these two circuits is the fact that in a parallel circuit, which is the name of this kind of circuit, you have resistors not connected through the same loop, but through different loops. So this is considered its own sort of loop, and this one is a different loop. This regards Kirchhoff's loop rule, which is a conservation of energy, which essentially just means that the current that flows through this loop plus the current that flows through this loop has to be equal to the total current of this entire circuit. So say you have resistor 1 and resistor 2, and this has a certain voltage V, okay? And you have a current I. Now, how do you find the current that goes here, which we'll call I1, and the current that goes here is I2? Well, since these two resistors are in parallel, it means that the voltage drop on either one has to be the same, because the voltage at this point has to be equal to the voltage at this point and at this point. So that means that the current, we'll say IN, which is the number, is equal to the voltage drop, well, negative voltage drop, is equal to the negative voltage drop times one over the resistance N. So it's just equal to negative V. We'll call this V drop N, or we could just say negative Vn over Rn. Okay? So that is the current that will flow through here. And how do we know what the voltage drop is from here to here? Well, this voltage drop has to be the same here to here, here to here, right? So then you would say, okay, so that means that this voltage drop is the same as this one. And since there's no other resistors in the circuit, this is the only one here. So we can calculate the voltage drop, because since these are the only resistors, it goes from V to 0. So from V to 0, because there's no other resistors. If there was another resistor here, we could calculate, we could calculate the voltage drop of this resistor, which we'll call R3, voltage drop 3, or we could just say V3 is equal to. So your voltage drop at the third resistor is going to be equal to negative R3 times the current. And that's the total current, by the way, since this resistor is actually in series with the battery. And so, since we know that this resistor is the final resistor, we know that this has to be 0. So then, since this is the voltage drop here is V3, we know that this one has to be V3. So then this has to be equal to also V3. So now we're going from V to V3. And how do we calculate the total resistance of a parallel circuit? Well, the total resistance of a parallel circuit is equal to an inverse. So it's actually 1 over the total resistance of the circuit is equal to the sum of 1 over the resistance of each resistor in the parallel circuit. And so what does that mean? It means that we have finished our electricity unit review, and that will be all for this AP exam review. And hopefully tomorrow, or if you're watching this in the future, you will do well on your AP Physics 1 exam.